So, next speaker is gonna be Itahiza Francisco Domínguez Cerdeña. Itahiza Domínguez is from Fuerteventura at the Canary Islands. He's finished his PhD in physics in 2004 in Göttingen in Germany. He's a seismologist at the IGN since 2007 with a special interest in volcano seismology. He has worked actively in the volcano monitoring of the two last eruptions at the Canary Islands. The first one was Tagoro Submarine Volcano at the island of El Hierro in 2011, and the second one at La Palma in 2021. Itahiza, please.
So I will talk about how we do volcano monitoring, since I work in the Geographic National Institute, which is responsible for the volcano monitoring in Spain. And I will talk about how we did the volcano monitoring in the last two eruptions in the Canary Islands, the Tagoro eruption and La Palma eruption 2021. By the way, I don't call the eruption with any name because we don't have an official name. Even some people are using Tajo Gaiter or other names. I will use always La Palma eruption 2021. Just because as IGN is responsible about the official names, not give the names, but say what is the official name that has been given, in this case should be by regional government, there is no name, and I will say always La Palma eruption. So, how we do volcanic monitoring? We need to answer two questions. When is going to happen the eruption? Of course, we want to know when it will start, and how is going to be the eruption. So to know when, we use the precursors, I will show you next. And usually we don't give just a date, exact date. Usually we give a window, a time window, and with some probability. And we need to know how it's going to be the eruption, because we can have an explosive eruption or an effusive eruption, and we need to know what can we expect. But in Canary Island we have another problem, because I show you here a map of Tenerife with the last 10,000 years eruptions, in this case only basaltic eruptions in the island. And you can see that we can have almost eruption everywhere. This is like a 70 kilometers long island. So we have many places where you can have eruption. You have some preferential places, in this case the rift from northeast and northwest, and also in the south part of the island. So we need to answer another question, and it's where is going to happen the eruption. So we have a new unknown that makes this volcano monitoring even more difficult. Usually when you hear a volcano that you know, like Etna, Popocatépetl, or other volcanoes, they know where more or less is going to be the eruption. Here we have a big unknown in this case. So how we do that? How we know the state of the volcano? We need to have three parts. First one is the geology, of course. The volcano is the main part is the geology of this volcano. Then we have the observation of the precursors that may happen before or during, before the eruption, and also what we have during the eruption. And then we have the modeling. The modeling tells you what is going to happen in the eruption. So the geology, for example, gives you how it's going to, or more or less can tell you how it's going to be the eruption that you will have. And this is just knowing how were the past eruptions in your place. Also, the geology can give you information on how is going the eruption. Studying the rocks, you were seeing in the Nieves presentation that they were sampling the rocks, and we did the same in La Palma eruption. You know how is the evolution of the magma chamber, for example, or the lava that is going out. Also, the geology put together all the puzzle pieces from the observation that you have. Then we have the observation. The observation has many techniques, but I will focus in the three main that we have: is seismology, geodesy, and geochemistry. In the case of geodesy, geodesy measures the deformation of the surface. And why we have deformation? Because we have a magma intrusion coming from below an island, for example, and you have the crust full of rock, and suddenly you have a new material that is going up. So when you have this material going up, you will have deformation on the rock, and then you can measure it on the surface. And there are different techniques. I will go only the two main techniques that we use. The first one is the GNSS, the Global Navigation Satellite System, or the GPS, the American GPS. This is the same that you have in a mobile phone or a car, but with more precision. With these techniques, we apply measurement of the time difference between signal that come from different satellites, and you can have a precision even of 2 millimeters. This means that if you have GPS antenna like this one, you can measure the movement of this antenna with a precision of 2 millimeters. So we have a network, for example, in the island. This is the network that we have before the eruption in La Palma, and you can measure how these antennas are moving. Usually, if you have a magmatic intrusion, what you expect is to have somehow radial movement from the center of this intrusion, but this is not always like this, but this is a nice example to see how it's usually the deformation that we have. You can see here that this is only 1 centimeter, and some of these deformations are just 2 centimeters or even lower. And also you can model what is the magmatic intrusion that you're having below. Also, another example that we have is the INSAR. I think Nieves also told us a bit about this. It's just you have a satellite that is measuring, sending a radio signal, and you can measure the difference. If you pass different times, the satellite pass different times, you can measure the difference between one time and another, and you can measure a slight movement on the surface. Usually the precision that it has is of the order of 1 centimeter, but the advantage is that you have, with the GPS, you only have some points where you can have a GPS antenna, but the inside you have a 2-dimensional map of the deformation. No? In this case here, you have this deformation on a volcano. The seismology measures the earthquakes. When you have a magmatic intrusion, this intrusion tries to push the rock, and the rock is not fully elastic, so you will have some cracks, some fractures on the rocks, and these are usually the earthquakes that we can measure. This is an example of a seismic swarm in El Hierro. This is 1 hour of seismicity with, as you can see, tens of earthquakes, and we can have even 100 of earthquakes in 1 hour before an eruption. For this, we use seismic stations. Usually we need to put these stations far away from the population because we want to avoid the cultural noise. In fact, this station is situated in Pico Viejo. It's 3,000 meters above sea level, very close to Teide volcano. And then we have a seismic network, and with this seismic network, we can locate the earthquakes. The location of the earthquakes usually somehow mark where is the magma going. Not always, but somehow it can tell you this information. Here, for example, we have a swarm before the eruption of Badabunga in Iceland in 2014, and you can see in this case how the magma migrate horizontal. In this case, we have like 12, 14 kilometers migrating at 6 kilometers depth, and you have a migration, horizontal migration, and then finally we have an eruption in this place. So again, we have the seismicity. So the seismicity is somehow telling you where, more or less, is the magma. It's not always telling you exactly the position, but gives you some information. In this case, the intrusion started here, and finally we have an eruption in this place. And we will see that we have something similar here in the Canary Islands. Finally, the geochemistry measure the gases that are coming from the volcano. I think also you have seen some things from Antonio. So the magma usually has some gases inside the melt, and these gases come out in different ways. For example, through the fumaroles. These are the fumaroles that we have in Teide volcano, and we can measure the composition of the fumaroles. In this case, Teide volcano is having all the time magma gases coming out because we have a magma chamber. So measuring the composition of these gases, we can see changes in the magma chamber. It's not working. Oh, okay. Then we have also from the volcanic plumes. In this case, this is a photograph from the volcanic eruption of La Palma. And also you can measure the gases from the volcanic plumes, so you can see also the state of the eruption, the state of the magma that is going out. And also you can have gases that contaminate somehow the underground water. In Tenerife, for example, we have an aquifer, and we can measure the gases that are dissolved in the water to check changes also in the volcanic system. And usually, as it says, gases or magmatic gases come out first before an eruption, even before the seismic activity. Finally, in the volcano monitoring, you need to do models. In this case, this model is in fact a hazard map for the whole island of Tenerife with the probability to have a lava flows. This is taking into account the different eruptions that we have had in the island in the last 10,000 years. But also you can give a model of just one eruption. If you have one eruption and you know the position, the beginning of this eruption, you can model where is going to flow the lava. In this case, this is a lava flow modeling, or a lava flow scenario, and the red gives you the more probability. So if you have an eruption here, this lava flow probably will go here, but you can have other probabilities that go in other directions. So this is very important for the silt protection to know which, for example, which village must be evacuated when you have an eruption. So just let's begin with the first eruption. This was the Tagoro eruption in 2011. It has, as Antonio told us, 3 months more or less of precursors. Began on 10th October 2011. It was a submarine eruption. This is very important. As you can see here, this satellite photograph. And it lasts for 4 months and some days. This is the precursors that we have before the eruption. 3 months of seismicity and deformation. We have, as you can see, a seismicity that began in the north and migrate to the south. So at the beginning, we even thought that the eruption will be in the north, but the eruption finally was here, in the south port of El Hierro, close to La Restinga village. And the arrows show you the deformation, how the deformation began in this way, and then migrate. Since the magma, there was a migration to the south, you have a deformation to the north. And we have about 10,000 earthquakes before the eruption, and at least 5 centimeters of deformation. Then on 10th of October, we have a beginning of the eruption with a tremor, a volcanic tremor. This volcanic tremor gives you, is produced by the magma somehow going out through the rock. So this is the reason we know that this time we have this beginning of the eruption. The first signs that we the first signs that we saw were some dead fishes because of the flux of gases and everything. The fishes ran away from the place of the eruption and they just died because of the change of pressure. Also, we have some stain on the water. You can see here better. We have a stain. This decoloration of the water was produced by the sulfur of the gases of the eruption, and even we can see some ashes coming out from the eruption. This is the stain, the sulfur stain, and here you can see this gray stuff or brown stuff is the ashes. Also, the gases directly from the eruption. You can see here the oceanographic vessel, very small there. Also, we have some rocks that came out from this eruption. In this case, floating rocks. That is something a bit strange to see, but in this case, we have these restingolites. This was some rocks that were composed in the inside part by a white stuff that was very light. This was a stuff, a rock that found the basalt. The basalt is the black part of the rock, so the basalt came out and found this white stuff. I will not discuss which is the origin of this stuff because there are different theories. But they found this rock and they go out. So this rock was so light that the final rock, this let's call they were called restingolites because the Restinga village was very close to the eruption, and these xenopumides went out and floated in the water for a long time. But after 1 month of eruption, we start to see these rocks. These were lava balloons. So imagine a balloon that is surrounded by basalt and is empty inside, so it can float for a time because it was so hot inside. You can see the water vapor going out because it was so hot inside that the water cannot go inside. And these rocks were even 2 meters long. So you can imagine how strange was that. And here you can see the empty part of the lava balloon. You can see some white stuff here, and this is because of the salt of the water, because the water tried to go in, evaporates, but the salt of the sea stay there. Finally, the eruption ended in somehow February of 2012, but the next 2 years after the end of the eruption, we have had 6 magmatic intrusions at least below the island. Here in orange is the seismicity, the precursive seismicity on 2011. The red one is the seismicity during the eruption, and then the other colors show you different magmatic intrusions that happened during the next 2 years, from 2012 to 2014. And they were even more energetic than, some of them were more energetic than the actual precursor of the eruption, but there was no eruption during these magmatic intrusions. But of course, this must be monitored and was, of course, activated all the plans, the seal protection plans and everything. Finally, let's talk about the La Palma eruption in 2021. In this case, we have a big difference with the eruption in El Hierro is that the precursors lasted only for 1 week, while the precursors in El Hierro eruption, in Tagoro eruption, last for 3 months. The beginning of the eruption, the duration was about 3 months. Also, we have some pre-activity, not really precursors, but some pre-activity 4 years before the beginning of the eruption. We have some seismic swarms, very low magnitude, low number of earthquakes, and at a depth of 20-30 kilometers. Now we know that this was like a preparation of the magma that was going up from the mantle, probably. And on September 11, there were some earthquakes, but on September 12, we have all this seismicity. This is a spectrogram of one station in La Palma, and you can see how from the morning to the night, we have an increase in seismicity with increasing magnitude. On September 14th, we saw the first deformation. We have here the arrows from the GPS antennas, from the GNSS, and you can see how we have a deformation of 2-3 centimeters. We also have some deformation measured in a tilt meter, so the inclination here, the tilt was about 3 microradians. It's very low, very low tilt, and we have some seismicity at the beginning at 8 kilometers below sea level. Then we have also the INSAR measurements, as I think as Nieves already showed us. These INSAR maps give you a 2D map of the deformation, and we have, at this time, it was September 16, we have some 10 centimeters deformation. And in fact, the comparison with the seismicity at this time, you can see how we have the seismicity here. The seismicity was a bit north from the deformation. So as I told you, the seismicity is not always telling you where is the magma, but more or less gives you an information about that. And at this time, magma probably was a bit southern from the seismicity. Then on September 19th, we have a final migration to the surface. We have here some seismicity until the morning of that day, and then at 10 a.m. we already have this cluster here that is, well, you can see more or less at 2 kilometers below sea level. And the deformation, you can see here now the deformation, and we compare now from September 16, this antenna was just going up, in fact, and here we have going to the south. So we have a migration to the north, that is clear. Here I show you a movie with all the seismicity and deformation, so you can see how evolved the seismicity, how the seismicity was going up, and the deformation. I will show you again now. And even before 3 days before the eruption, we start to see some surface, some shallow seismicity. We think now that maybe this was produced by the deformation, not by the magma. Here I will show you again. Let's see. This is in the movie. It's nice to see how the migration of the seismicity marks you more or less the position of the magma, and then just the eruption began here. Then, when the beginning of the eruption, again, we have a volcanic tremor. When you have a basaltic eruption, the beginning usually is accompanied with the volcanic tremor. And here is a movie of the first 2 minutes, I think the minute 2 of the eruption from Stavros, who is here. So you can see at the beginning we have a lot of ash going out. As Nieves told us before, this is a fissural eruption because we have no I mean, the magma go in the basaltic eruption here in the Canary Islands usually go out not through a tube somehow, but through a plane. And in this case, the plane in this eruption was about 200 meters long. So we have different bends because of this fissure that was open at the beginning of the eruption. Finally, we have a main cone that was the main vent that produced the lava flows. This is all. Probably I missed some things that we do during the eruption. What is the monitoring during the eruption? Because you don't only need. I mean, it's not only necessary to do monitoring before the eruption. This is important, but also during the eruption. And we have monitored the seismicity, the formation, plume height, eruptive dynamics, everything here. But also, we have been in the PVolca, in the civil protection plan. We have given information. You need to, for example, to talk whenever they ask you about fake news and everything, you need to be there to do divulgation of the information. So this is very important. Here, this was the eruption, more or less at the end. I'm just going to show you one movie just to let you understand that how complex was this to work and to understand how was the dynamics of this eruption. So you need to know which changes would you have. I remember when Nieves told us also they have the drones. With the drones, they can measure the position of the lava flow. So this was very important for the civil protection. And also we did some of this kind of work to understand what's going on and which hazards do you have. Also, we have a lot of seismicity, and in fact, the in fact, we have high magnitude seismicity during the eruption. You can see here the colors. The orange is 2 to 3 magnitude 2 to 3. This is 3 to 4. So we have higher magnitude earthquakes during the eruption. Seismicity was located at between 10 and 12 kilometers, and also between 30 and 40 kilometers. So we have now somehow the path of the magma. Probably the magma was located here during years, and finally we have a migration to the basement of the island, which is 10 kilometers below sea level, and then you have the migration here in blue. This is the precursor activity. Also, we did a lot about measuring the deformation during the eruption. We have some peaks in the deformation that seems to be related with the activity that they had the eruption. We are studying now then, because in future eruption this could be very interesting to forecast different aspects of the eruption, different changes on the eruption. Also, the modeling, as I told you at the beginning, the first day of the eruption, we have this model. This is a model. This is La Palma. This is the place where the eruption began, and this is the model of probability of having lava flows. And this was the actual lava flows that we have. So this was almost a 100% success on the forecast of the lava flows. So this was, as I told you, very important for the civil protection to make the evacuations and everything. Also, we measured the volcanic plume height. This is important to if you need to close, not us, but the Volcanic Advisor Center may close an airport or give the advisor to close an airport. So La Palma Airport, that is more or less here, was closed many times. So for this advisor, you need to have the plume height all the time. So we measure this and we give this information every time we can. Also, we did some sampling, as already Nieves showed us. You need to do the sampling on the side of the lava flow, and you can pull down to preserve the volcanic material. And here, just to show you the sampling and the size of the volcano and the size of the lava flows. Just to let you know how was the comparison between the people that was working there and the actual volcano. Well, this is just people working close to the volcano, deploying instrumentation. And just at the end of the eruption, we have been working, of course. This is not working. No, it's working. So we have been working on the crater of the volcano to measure how is decreasing the gases, because of course the eruption ends, but you have a lot of the gas in there. It's very dangerous, and you need to study how is this evolving, the temperature and everything. And that's all. Thank you very much.
Itahiza, thank you so much. That was such an interesting talk, and I'm sure as you're going to be around later, there are some more general questions that we will be able to discuss about your role and IGN, which will be really interesting. But in the meantime, does anybody have any quick questions about the actual talk? Great. Let's choose somebody who hasn't spoken yet.
Thank you. Going back to Tenerife and the monitoring that happens on there, in your opinion, is there any way to improve the monitoring to help predict future eruptions?
I mean, we haven't, well, in fact, I didn't tell, but of course, from Tagore eruption in 2011 to 2021, we have improved very much because we understood, for example, that you need to have more automatic systems. And now we realize that this is even more important because you can have so short precursory activity. This is 1 week. We know that in other places in the world, you have even hours of precursory activity. So you need to have the more automatic, the best to be able to have a fast reaction to this kind of signals. Of course, there are many things that can be improved. I mean, I think we will discuss in this afternoon. But this automatic measurements, this automatic analysis, I think this is the key that we must focus in the future, and that we have tried and focus in the last years, and now we realize this is our force should be going on this direction.
Okay, thank you.
So thank you very much indeed. Any more questions? Just a very brief question, because then we will pass to Eugenio. Thank you.
Okay, thank you. Is there any changes in the subsoil temperature that can be detected by infrared, for example, as an indicator of an imminent eruption, or in the deformed area, so it's possible to locate where the eruption is going to take place?
Yeah, of course. I mean, there's supposed to be maybe sometimes minutes or hours before the beginning of the eruption. There should be some thermal signals, but it's very difficult to know, because the problem that we have here on the location of the eruption, so this is important to locate the eruption. Probably this could be done very quick with a satellite, but nowadays it's not really possible because of the resolution of the satellite. You need to go by helicopter, for example, trying to do some measurements, but this is something that also should be improved in the future, maybe to get better knowledge on where is going to happen the eruption. In this case, I know that they tried some flights to find the position of the eruption. It was impossible at that time. And I know that for some people, it's trying to get even the thermal signal that may come even years before the beginning of the eruption. This is a work that is being developing now. And some people are trying to get thermal signals, very low changes in temperature produced by a magma that is somehow cooking, you know. But I don't know how is the state now, and this is possible. But yes, in real time, this should be done, and this is something difficult, but can be done.
So thank you very much indeed. I think we'll wrap that up for now with you. There's so many questions. I know that we'll have some online as well, but we'll see you at the end of the day. But we wanted to just present our final speaker. Perhaps you might like to present our final speaker for us.
I would like to
session.
say, Sharon, if you let me, thank you so much, Itahiza. Thank you so much for your to your institution. Not only you, Stavro is here also, Maria Jose Blanco, Carmen Lopez. You have done a really great job, not only at the island of El Hierro in 2011, but also in La Palma. So thank you so much for your work and to be here today.